Okay, I think we're going to get going. So good day and welcome to all to our webinar, Electronic Records and Signatures, Rethinking 21 CFR Part 11 in a Graph-Based World. So today we're taking a fresh look at Part 11 and asking an important question. Is compliance just about logging user actions, or is it about demonstrating trust, traceability, and intent behind every record? We're going to explore what the regulation actually requires and where traditional systems that are relational based can fall short. And then we'll talk about why a graph-based architecture captures context from draft through to final signature by design. So throughout the session, feel free to drop your questions into the chat and we will address them at the end. So I'm pleased to introduce our first speaker, Brian Jack. Brian brings more than 30 years of experience architecting, designing, and implementing laboratory informatics systems with deep expertise in molecular diagnostics and pharma lab operations. So over the past 25 years in professional services leadership, he's helped life sciences and clinical organizations shape their informatics strategies, optimize technology investments, and drive measurable operational outcomes. He's known for applying modern software engineering principles and lean methodologies. Brian focuses on delivering tailored solutions that strengthen laboratory performance and scalability. Joining Brian is Megan Bowman, a seasoned product management professional with over a decade of experience delivering SaaS and LIMS-based solutions across life sciences, healthcare, and agriculture. As product manager for Labbit, she leads the development of platforms that support clinical diagnostics, R&D, analytical testing, manufacturing, and quality control. Megan has extensive experience implementing digital solutions in highly regulated environments, helping organizations streamline operations, enhance data workflows, and enable real-time data-driven decision-making. So before I hand you over to Brian, I wanted to begin by taking a quick poll. That is, what was sort of the motivation, or what are you hoping to learn from this webinar? And that should launch right now. There again, a few votes. Thank you. Thank you. This is all helpful. All right. Okay, Brian, do you want to carry on?
Yep, love to. Thanks, Riley. Thanks for all the kind words. Thank you, everyone, for joining us today. As Riley said, today we're going to take a fresh look at 21 CFR Part 11, which might seem a little odd because 21 CFR 11 Part 11 has been around for quite a while. It's been around for maybe 30 years or so. But with changes in technology, I think there's fresh ways to look at it. So today in this webinar, we're not just going to go through a checklist of features. We want to really take a step back and look deeper at the architecture. And what does it mean for an electronic record to really be reviewable, defensible, trustworthy? And how does the architecture really influence that? So today we're going to talk about electronic records. We're going to talk about electronic signatures. We're going to talk about the way that your system really models those things and how that change really matters.
And we're going to anchor this in the regulation directly, really dissecting what 21 CFR Part 11 actually requires, particularly around electronic signatures and their visibility. Our goal today is to provide a practical way to connect regulatory expectations to system design so that you have the tools to make informed decisions, but also know what questions to ask when you're evaluating platforms from this aspect.
All right, let's jump in. So most informatics systems that are in place today can generate an audit log. You could see that something in the system has changed. You could see when it changed. You could see who it changed, and so that's all great. I think just about everyone does that. But that doesn't automatically mean that the entire life cycle of what's happening in the system is crystal clear. In many cases, understanding what really happened requires reconstructing the timeline from fragments. So it's almost like you need like the magnifying glass. You have to really look to see at the audit to try to put together a story about what really happened in your system. And that's fine and good. But when you're in a high pressure situation, when you really need to understand what happened with your data, when you're in an audit, when you're defending a result, uh, that could be a risk. And the ability to easily be able to understand what precisely happened to your system and why it happened really, really matters.
And also, from a QA perspective, recording that an event occurred isn't always enough. We also need to be able to demonstrate the state of the record when that event occurred, especially when an electronic signature was applied to the record. An audit log can tell you that a field changed, maybe who changed it and when it was changed, but it doesn't necessarily tell you what the record looked like at that point in time, what version was reviewed, and what the exact record state was when the signature was bound to it. In an audit, though, those details do matter. Auditors will ask what changed and compared to what. What was the state before? Who reviewed it and approved it to change to that new state? And what was the record state at the time of signature? And was it locked after? If you have to answer those questions by joining together audit tables or reconstructing states across different timestamps or inferring versions after the fact, you're adding an extra interpretive step between the record and the evidence. That increases the time not only to demonstrate compliance, but it also increases the risk of inconsistent interpretation. To solve that cleanly, we need to go back to the source, back to what the regulation defines as an electronic record. Okay, so I want to call attention to the verbs in this definition of an electronic record, excerpted directly from the regulation. Created, modified, maintained, archived, retrieved, distributed. This isn't describing a static value. It's describing a life cycle. So when we talk about electronic records, we're not only talking about individual change events, such as field level deltas. We're talking about a sequence of meaningful states, the transitions between them. These must remain intact and reviewable over time.
In that definition, Megan used life cycle specifically, and that's really the concept that's really influencing the way your system is architected. Can you really show the entire life cycle of your data over time? Data changes, records change, state changes over time in your system, and the system really needs to be able to preserve that change over time to be able to see it clearly from the beginning to the end. So, if that's true, then the question becomes, how does the architecture of your system represent those transitions and help you be able to see that? I think most informatics platforms, most LIMS platforms, really most enterprise systems today are built on relational databases. Relational database technology has been around for quite a while, 40 plus years. Those systems are generally mature. They can be powerful. They enforce strong constraints. A lot of great systems based on database. So this is on relational databases. So this, what we're saying, is not really a critique of relational technology. It's proven. That being said, relational databases, when you build on them, force you into a way of thinking and a way of organizing information. And it's basically that way is tables and rows. So as you can see in the diagram here, a relational database has certain tables. Those tables represent certain concepts. Each table has rows, and those different tables are related to each other through inferred foreign keys. In other words, you'll put an ID number in one table, you'll put a corresponding ID number in another table, and that you're inferring that a record from one table is related to a record in another table. If you really want to be able to see the data together in the different tables, you have to do what's called a join, and that can be done multiple ways, but generally it's done with a SQL query. And so this is an example of a SQL query that binds together rows from different tables in order to provide kind of information about what's happening with a particular sample. And so in this case, in order to see the picture of the sample, you have to reconstruct it from this view. This table structure, this view, this is all pretty simplified, but this is the basic gist of how relational databases think about data. Different tables, you have rows across these different tables, and you have some sort of query that joins all of the information together. That could come from a sample table, could come from a history table, user table, a signature table, maybe even a table that maintains what the current status or the current state of the data is. Most relational database systems handle this and can track all this, and it's really powerful. But to see the history of your data change over time, you in essence have to reconstruct it using the data from its audit log instead of seeing it clearly. And when you have to reconstruct it and you're, for example, in the middle of an audit or something along those lines, that creates friction and that creates some uncertainty that you're going to get the right data. The history of what's happening in your system in a relational database exists, but understanding and putting it together means work that you have to do. And so that's a problem. The system stores events well, but the model for it is of how information relates to each other is not a first-class concept in a relational database. And that point is exactly where electronic records come in. So, what if you used a different technology? What if there was a different way of being able to represent the relationships in your data and be able to see data change over time better? And that's what we're talking about next. But before we do that, before we go and talk about changes in technology, I would like to take another poll. So this time, I would like to ask, which of the following changes have you experienced in your current system? And we'll give a few seconds for everyone to be able to answer that question. Riley, maybe you can just tell me when we have a good representative section there.
Will do. These ones are a bit longer, the answers, give people a bit of time to read them.
That sounds good.
Okay, I think you can continue, Brian.
All right, thank you. Okay, so we talked about relational databases being the sort of the main way that systems record data. Now imagine instead of organizing data in tables and reconstructing relationships, having inferred relationships, you can use a graph database. So a graph database is a different type of technology for storing data. And a graph database treats relationships between things as first-class citizens, not things that you infer. If you look at the diagram on the left of the screen, this is a representation of how graph databases represent data. Instead of rows that are in a table and tables related to other tables, what you have in a graph database are nodes. So a node can represent whatever type of entity that you would like it to be. It could be a sample, a single sample. A node could be a single patient, a single test, a result, etc. In a graph database, you have something that are called edges. Edges connect nodes, and an edge represents a relationship between nodes. And those relationships can mean whatever kind of relationship that you want it to be. So for example, you could have a relationship between a sample node and a patient node. You can say a sample node is from a patient, and that's the relationship between the sample and patient. Or you can say there's a relationship between a sample and a test. A sample has a test. That's a type of relationship there. So that's one type of relationship. Another type of relationship is what's called a revision relationship. So when a sample, say you have a sample node, let's say that sample node changes over time, you can have one node that represents that sample at one point in time. You can have another node that represents that sample at a different point in time, and the relationship being that that's node 1 was revised to be node 2. And that's how a graph database tracks status changes over time, those kinds of state transitions, by having different nodes for each point in time and a relationship between them. It's that relationship. It's really defining that relationship between those nodes that forms the timeline of what happens to your nodes, to your data over time. That means in a graph database, you don't have to reconstruct history. You don't have to reconstruct from an audit log what happened over time. You can actually traverse it by going to the beginning, the first node, and looking at the relationships over time and watching them change. To make this maybe a little bit less abstract and more clear, let's look at this in the lens of the definition of electronic record. So we said before, the electronic record is a combination of information that's created and modified over time. If we model that concept in a graph database, you have an interesting way of looking at it. So again, let's look at the left-hand side of the screen here. And this represents a progression of data or a progression of state over time. So that first box represents, let's say, the initial node of a sample. So you have a sample, it's revision 1, it has a certain status associated with it with no results. Over time, you're going to process that sample. And so now you have revision 2 of that sample. It has a different state. Now it's processed. It also has a result that's entered against it. So you have 2 nodes. Node 2 represents that version at that point in time. You can have a third revision of it. This time, maybe it's been reviewed by somebody and electronic signature has been applied. So now you have 3 nodes. And you can see the transition from node 1 to node 2 to node 3. And it's that transition which is so powerful about the way that a graph database tracks this and the way that it maps electronic records. That's the transition that we care about. That's the way that life cycle is maintained within the database. And that is exactly what an electronic record must preserve. So in this model, in this way of thinking, in a graph database world, and how it maps electronic records, we're not concerned about changing a specific field. We're concerned about capturing the state of what your data was at one point in time, making changes to it, and then being able to capture what the state is another point in time, and being able to point to exactly what the changes were. And this way of modeling data in a graph database aligns very, very cleanly with the kind of language that Megan shared with the electronic record definition. It's very much aligns with the life cycle verbs in the regulation.
Yes, and this is important from a compliance standpoint. So when auditors come in and evaluate records, they're evaluating what was the state of that record when it was approved, who approved it, and what information was present at that point in time. If you can clearly show that state and its evolution, this review becomes much more straightforward. So how do we control that transition in a compliant way? State transitions aren't something that should require manual intervention or recollection from the user. They should be enforced by the system by intentional design. So going back to the regulation again, Part 11 calls, quote, for use of operational system checks to enforce permitted sequencing of steps and events as appropriate. At the highest level, we're defining the order of work or the permitted sequence of tasks that operators can perform using an integrated BPMN workflow, as shown here in the top left slide of the slide. Each task defined within that BPMN produces a contained unit of work that we call the workbook. The workbook is what establishes the boundary for an electronic record. We're going to talk more about having a clear boundary for workbook or for records and for signatures. So I just want to emphasize this is where we're creating that boundary. This is where we're defining through configuration what this record will include, what entities will pass through it, what entities are produced upon completion of it, what data is captured as part of that task, and what process metadata is captured during its execution. This is where we also define the state control. So we've been talking about states. This is where we can actually define what states are part of this electronic record. As we see in the other screenshot here, we're also configuring what signatures are required. Do we just need an editor signature, or does this also require an independent reviewer or an improver? As soon as we define this, we've defined the intended lifecycle states this workbook will move through. In this case, in progress, needs review, completed. So BPMN controls the sequencing of the tasks and the work, and thereby the workbook order. The workbook configuration controls those state transitions within the electronic workbook itself. From a compliance standpoint, this distinction is exactly what makes this defensible, this record. Part 11 requires system checks that enforce the permitted sequencing of steps and events. BPMN is the system-level control governing what can happen next. The workbook is the record-level control. It's governing when the step is complete, what must be reviewed, who needs to review it, in what order, before all of that can be finalized in the record. This makes the audit trail structured and meaningful and demonstrates clear progression through these defined states. All right, so let's take a moment to walk through what's actually happening from both a user perspective and the database. If we look at the top right here, we see progression of a workbook state, the 3 iterative screenshots. As we can see with the topmost one, this workbook is beginning an in draft in progress when it was first created. It's at this stage we've created a very controlled workspace to enter data. We are preparing the next proposed state of this record. Once our data entry is complete, we then initiate the necessary review and approvals by requesting signatures. Accordingly, this workbook now transitions into a review state, which we see in the middle screenshot. Based on the configuration that's been defined for this particular task, specific signing reasons are requested only when prerequisite signatures have been satisfied. We're enforcing that state control. Only when all required signatures have been collected can the workbook be completed and subsequently committed, as we see in this final screenshot in the frontmost view.
In that screenshot, especially where you see electronic record created here, that signifies a pretty important thing that's happening in the database. So just like a relational database, graph database, we have the concept of committing data, which is the saving the data to the database. When we commit data to the database, it means that a new revision of the nodes are created in the database. So new revisions of the data. We don't update existing data. We create new revisions of the data. Each revision is immutable, meaning it cannot be changed. The only way to change it is to create a new revision of it that has the change that you want associated with it. And so that's what this electronic record created here symbol means in the history view here. It means that is when the data was committed to the database, and that becomes electronic record. So electronic record isn't the draft. It's not the intention that I'm going to be making changes. It's when you commit the data. In this case, there was also a signature event that occurred with it. It's committed to the database. New revisions created. Now that is the electronic record. And you can, if you go in the database and look, you can see that these things all happened, who did it, when they did it, etc. So the commit creates a new graph node, some new immutable state of the workbook, and it's permanently linked to all the prior revisions. Again, we have relationships between all the different versions, and you can see what those relationships are. The transition is between them and is preserved. And so this aligns directly with the model that we introduced earlier of what an electronic record is in the state transition. Within this particular screenshot that you see on screen of Labbit, you can see all aspects of the history of the workbook. So when the workbook was created, when a review was requested for it, you can see who may signed it, why they signed it, when it was finally committed for saving to the database. And that's the electronic record. All of that information stored directly in the database itself in a way that cannot be modified. And because the commit happens after the required signatures are satisfied, the record is set. All data is there. All the approved data, all the required roles, all the reasons, all the enforced sequence is all built directly into the workbook and stored in the database. And that's what makes the electronic signature meaningful. The signature isn't floating on a draft. The signature is bound in an immutable way to the electronic record of all the data that's committed in the database. It's not something that can be separated from the electronic record. The signature is bound directly to that. And that happens at the commit. That happens when the data is saved. And that is kind of this moment when electronic record is created, the data is created, the signatures are bound, and it's atomic.
Great segue, Brian, into a little bit more detail on the signature. So it's not just authentication; it's actually a legally binding action and reflects the equivalent of a handwritten signature. So this means two things in our context. First, it must be attributable to a specific individual, and it also, as Brian talked about, must bind to a specific electronic record. If the boundary of that record is unclear, the signature boundary becomes unclear, and there can be ambiguity around what the signature attests to. And that's why we spent a lot of time detailing around the workbook actually creating that boundary in the previous slides. It's actually creating a clear boundary for which the signature can then be bound to.
And that's why we're having this discussion. So I mentioned at the beginning, 21 CFR 11 has been around for a while, but it's this application of the new technology of the graph database and Labbit's application of it, which is new, because it's a new architecture. It's a new way of being able to ensure that we're meeting the regulations as they were intended. If you apply signature to records in your system, but you don't have that boundary, that you don't preserve the state of the record at that moment, that you can't tie a signature to all the data together, then you don't really have an electronic signature the way that the regulations intend. So imagine you've got a piece of paper with a bunch of data and a signature at the bottom. You cannot remove that signature from the rest of the paper and the data. It's all together in one kind of binding together. And that's what we're talking about. That's what this graph database and Labbit allows us to do that a relational database doesn't. In a relational database, you may have a signature data stored in a signature table somewhere. You may have an inference to data in another table, but it's not all bound together in the way that we do in a graph database. And so it's this revision-based model that's really the heart of making sure that we have immutable state data all together all the time. And one other thing that is often overlooked when you talk about the regulations of electronic signature, of electronic record, is that once you sign the data, it needs to always be visible when looking at that data.
The regulation doesn't only stipulate that signatures must be present and used. It also defines how they must appear and what they must contain. So if we look here at this excerpt, again, directly from the regulation, printed name, date and time, meaning, and critically, it must be included in any human readable form of the electronic record. That means if someone views it on the screen, if they print it, if they export it, that signature manifestation must be visible right on that record. If the signature isn't visible, it's not compliant.
And again, this is where the architecture of your system matters, because your architecture can make that, what Megan just talked about, easier, it can make it hard. If your system stores signatures in a separate table or only logs, certain events in an audit table, and you need to dig through the audits to see who signed and when they signed, and you separate your data from your signatures, for example, you've stored what's happened. You could recreate what's happened, but you don't really have a proper manifestation of all things bound together. And in a revision-based model, signature binding with a specific version, that's what graph will give you. So we've talked a little bit about graph. We've shown some elements of Labbit. Let's make this real and show how this is really implemented in practice.
Yes, so this slide shows how that requirement is fulfilled by design of the system. On the left-hand side here in the screenshot, we are defining what electronic signatures must be visible for any record that's produced from executing this given task. So this is where we're establishing not only the high-level intent behind every required signature, such as editor, reviewer, or approver, But we're also defining, we can see in the text that is highlighted underneath the reason for signing, we're defining a more detailed contextual reason that further aligns to the regulation requirement for giving intent and meaning to your signatures. And we're doing it in a controlled way so that this is now captured as part of the data that's recorded with the signature. What we've defined in the configuration on the left will then be displayed when the user goes to add their signature, as we can see in the center of the screen. They're signing with intention and meaning. In this case, they're signing as a reviewer, and they have the context, the specific context related to the work that they've done in this task as part of what they're signing off on. So the signer sees the high-level reason for their signature, the specific context as it relates to that task and what that signature attests to, and the record to which they're binding that signature. This aligns directly with the regulation's requirement that the meaning of the signature must be clearly indicated.
So on the previous slide, we saw how the signature parameters are defined in the configuration and then executed. So let's take a deeper look at what happens to that actual signature data. And we're going to do that by looking at the workbook history here. So if we look here, the final entry in the history, which is at the top, says workbook completed. In that model, what that means is there's a committed state. So the new node was committed to the database. That's the current node. We've revised previous nodes. So that indicates data stored in the database. And this is really, when you think about it from workbook, this is the moment that we're building towards, that the proposed state becomes official. So we've started a workbook. We propose we're going to make these changes. We sign it. We say we're finished. And now we have a new immutable revision created in the database that represents the work that we did. The electronic record represents the change that we made. And it becomes a new revision. We don't overwrite it. What happened before, that exists, we preserve it. That history is always there. It's easy to see. We now have a new revision that represents the electronic record of the change that was made. If you look at the other entries in the history list, you can see that there's all kinds of other work that happened on the workbook. You can see that that a review was requested. You can see when it went in progress. You can see the whole history of that particular workbook that ends with the committing of the data and the saving to the database. So what you're seeing really isn't just an activity log. It's really state transition of status. So a workbook starts in a draft. Maybe data is entered. You review it. It goes in progress. You review it again. Maybe there's even a signature in there. So different states, you commit, and all that change is recorded fully in the database as the electronic record. And let's say there was a signature. You can see at the top, the screenshot at the top, that there's a couple of different blocks there that represent the different signatures, electronic signatures that were applied. So in the top left here, we have the contributors or the editors. So those who made the changes to the data. On this particular configuration, we asked that they provide a signature. And so we have the information about when they performed their changes and when they signed. We can also have a reviewer, a second person reviewer, who can review it. And then finally, we can have an approver to do that. And we can record each of those electronic signatures in the system, of course, when it happened and who did it, but also the reason for it happening as well. And so all of that is bound to the electronic record in the database. It's not separate. You don't have to issue a query to see it. It's attached to that specific committed state, to that specific revision of the data. And that's really the core idea that we're talking about here, is really having a strong definition of what an electronic record is that aligns very well with the regulations, and making sure that its state is always known, and making sure that the signatures that are applied to it are inseparable from the data, because they're all stored together on the immutable version. And that, in essence, is the core difference that we're talking about here in this webinar versus a relational model. In a relational model, systems generally do a great job of logging events and putting them in an audit table or something similar to that. You can probably reconstruct what happened in the life cycle by looking at the values in the audit table. And on the left-hand side, that's what we're trying to indicate there. You can reconstruct it, but that's what it really is. It's reconstruction. You're looking at fragments over time and trying to pull together a view of what exactly happened over time. The data is all there, but it's a bit of forensics to pull it all together to make sure that you can really show exactly the history. It's powerful to record all that data. That's really useful. But when you need to pull it together to see exactly what happened, you're doing a bit of forensics work to pull it all together. In a revision-based graph model, it's no forensics, it's just explicit. This view on the right-hand side is a view from Labbit, and I would say it's my favorite screen in all of Labbit, because it very, very explicitly shows you the history of whatever it is you're looking at. So in this particular case, we're looking at a sample. Each of those gray bars represents a change that was made, whether it's the first creation of the sample, the logging or the sessioning, sample collection, sample preparation, maybe performing a test, etc. And you can see the transition from one change to the next as the data changed over time. So each of those gray bars represents a state change, a separate electronic record. And to the right, for each of those changes, you can see what the data on that record look like, all the data look like, so that you can literally go from change to change to change and see the data. This was the data at this time. This is the data at this time. This is the data. This is the signature that was applied here, etc. So you're not piecing together history. You're telling a story. You're walking it down, and it is extremely clear.
Yes, and from a QA perspective, this is incredibly important. If someone comes and asks, what was the state of that record at that point in time or when it was approved, you don't need to reconstruct it. As Brian walked through that screenshot on the left, we can see that. It's all visible to us. So we don't need to go and put it together. We can be able to point to any revision at any point in time and say, this was the state, this was the signer, this was the time, and this was the meaning. And that's really what's making this a defensible record, and why the signature manifestation and the revision binding should not be uncoupled. Okay, so in summary, let's just go through how Labbit today enables 21 CFR Part 11, which has been designed directly in line with the regulation. We talked about how there's operational system checks in place that enforce the permitted sequencing of steps as well as state transitions. The system is governing what can happen next, and it's preventing completion out of sequence completion. Second, workbooks are what defining the electronic record boundary, which becomes very important to have that boundary scope so that it is fully clear what the signature attests to. Within that boundary, tasks can be configured to require specific signatures, whether that's contributor, independent reviewer, or approver signatures before committing the workbook. So the record cannot advance until all required roles have signed in the required sequence. As work happens, all node changes, such as entering results, are captured as complete versioned revisions, as Brian talked a lot about with the database. When someone signs the record, each signature captures the reason and the intent, and it's stored as part of that electronic record, right alongside the revision to which it applies. So when you go back and you review that record later, there's no need to infer why someone signed it. Its meaning becomes part of the signature itself. On completion, the workbook is committed to the graph as an immutable revision. And finally, workbook state history is always accessible for review. You can see the lifecycle progression, the revisions that have been created along the way, as well as the signatures that have been applied, together as one coherent record.
And this is what I really love about the way our technology works here, is because everything that Megan said there is really important, and it's enabled fundamentally by our underlying technology of how we use a graph database instead of a relational database, and how we structure workbooks. So all of that Megan talked about just sort of comes along with the architecture choices that we've made with this. You don't have to try to recreate history. You don't have to create custom pages to make it happen. It just comes along with the way that this works. These immutable revisions exist in the database rather than overwriting data. We don't have field level audits. We have complete electronic records of what's happened. You can't detach a signature from a record, not because someone says we need a feature to do that, because that's the way the architecture works. That's the way the technology works. It just enables what the regulations say. Okay, so as we wrap up here, just a couple of key takeaways that we have. If you remember nothing else from this, I think important things to remember are what really an electronic record is. Electronic record is not a cell in a table. It's not a row in a relational database. It's not a specific keystroke that someone made. Electronic record is a change, and all the elements of what that change are. It's a transition from one state to another state, and everything that belongs as part of that. And if your underlying technology of your system makes that really, really clear, then it becomes easy to review. It becomes very straightforward, and your compliance is just kind of handled manually or handled automatically.
And just to add on to what Brian is saying, we must also keep in mind that signatures must bind to that state from that transition. They must be visible, and they must preserve that accountability. And again, when architecture and compliance come together, this really helps us create a defensible record.
Okay, so we're nearly done here, but in closing, just a few questions that I urge you to consider as you're evaluating your existing Part 11 compliance for your existing systems or your needs in the future. So when you evaluate any system, whether it's our system or another system, I encourage you to think about these questions. So number one, do you have a clear record boundary? If you have that, between one revision and another revision, everything's easier. If you don't have that, everything becomes much harder. Number two, do you have to reconstruct the history of what happened in an audit? Or do you have a clear, unambiguous story, a timeline of exactly what happened from beginning to end?
And thirdly, what do your signatures bind to? Do they attest to that preserved state of the electronic record, or are they really aligned more to the metadata that has been captured within that record? And lastly, is the signed record immediately accessible? Can someone verify it instantly, or does it need to be reconstructed? Collectively, these questions go beyond just feature evaluation. They fundamentally branch into some of your architectural considerations.
All right. Thank you.
Thanks, Brian and Megan. We did actually get a question come in. So I'll let you two decide who to answer. It says, what is your approach for validating your graph database?
Sure. I can take that. So we do not, we don't think about validating the database independent of the rest of the application. And so I'm going to answer this from the perspective of how do we validate the entire platform? Because our graph database is, say, one component of the entire platform. And so we look at we look at this holistically from a validation perspective. And so we have specifications that specifically say what each of the components in our system do. We perform an installation qualification of all of those components to make sure that they are all installed properly. We have a series of course, of requirements for what the platform should do. And we have a set of operational qualification tests that we perform on every one of our every one of our releases. And together, our installation qualification and our operational qualification prove that the system is installed as it was intended, and that it's operating as per its intended. Now, and so that from a platform vendor perspective, that tells us that everything is operating correctly. As Labbit is used by our clients, by our customers, there's configuration, of course, that is done on top of that in order to set it to their specific, to really tailor it to their specific needs. And so there's typically additional validation that's done on top of that for their specific workflows. That additional validation leverages that platform validation that proves that all of our components are installed and working as per requirements and spec. So
Great.
I hope that answers the question. Happy to take additional questions on that.
So that's all the questions that we received from the audience. So you guys were very thorough in your presentation. I did have one more poll before we say goodbye. So we'd like to know if after today's session, would you be interested in learning more about Labbit? And I'll give everyone a couple of seconds to answer that. Okay, we're getting some votes. Wow. All right. I think we're going to wind down now. Thanks everyone for joining today, and everyone have a great rest of your week.
Thank
Thank you,
you.
everyone.
Bye.